Hey, welcome back to Fat Mama Physics. In this video, we're going to do example 3 of 6.2, part 2, which has to do with orbits. And for orbits, we have to relate Newton's universal law of gravitation to circular motion, in which the force due to gravity is going to be the pulling force, allowing the object to stay in circular orbit so it doesn't fly away. Okay, so let's begin with our example. A 4,500 kilogram Earth satellite has an orbital radius of 8.5 times 10 to the power of 7 meters. Okay, so key thing about orbital radius is whenever you see orbital radius, it's exactly the distance from the center of the Earth to the satellite itself. So you don't have to add the radius of the Earth on top of that. It's exactly from where the satellite is to the center of the Earth. This value here is 8.5 times 10 to the power of 7 meters, as said in the question. Okay, so then what are the forces acting on this object, allowing it to stay in circular motion? This would be its force due to gravity, which is Newton's universal law of gravitation. So here we have to write our F net equation, in which to solve for A, we're going to need that. Our F net is going to be our Fg, in which Newton's universal law of gravitation is big G times the mass of the Earth times the mass of the satellite, which I'll say is m, that's going to be m here, divided by the radius, the orbital radius, which is this guy over here, squared. And that force is going to be equal to the mass times acceleration, mass of the satellite. Centripetal acceleration is going to be v squared over r, because we want to find v, right? So that's why we do that. We notice that this rm here, the mass of the satellite, doesn't do anything. In fact, it cancels out in our equation. We also notice that there is a radius here from the center of the Earth to the satellite. This also is able to cancel with one of them on the other side of the equation. So all we're left is v squared is all equal to this whole thing on the other side of the equation, so that all we have to do is just take the square root, and that's going to give us v is going to be the square root of big G, mass of the Earth, divided by the orbital radius. So putting all those values in, 6.67 times 10 to the power of negative 11, mass of the Earth is 5.97 times 10 to the power of 24, and all of that divided by the 8.5 times 10 to the power of 7 meters. Let's put all that into our calculator. I get 2164 ... And that's going to round up to 2 sig figs, 3 sig figs, since we didn't even use the mass of the Earth satellite. So that's going to be 2160 meters per second. So yes, if it's rounded to 2 sig figs, it would give us that. But I ruled it out because we didn't use the mass of the satellite. Okay, that was A. All right, let's do B. What is the orbital period? The orbital period, we know we can graph from the tangential speed of the satellite as 2 pi radius time over the period. So to rearrange for period, I just have to swap the t, the period, with the velocity. That's just a bit of algebra. So I get the period is equal to 2 pi r over v. So multiply v up here, multiply t up there, divide v down here. And putting in all our values, we're going to get 2 pi radius as 8.5 times 10 to the power of 7 divided by our speed here, which is going to be 62164 ... no rounding. And putting that into our calculator, I'm going to get, and I get 246,750 ... blah 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 blah. And this is going to round to still 3 sig figs, which is going to be 247 and 000 seconds. Okay, so this in my key, I rounded to 2 sig figs, should be 3. So that's it. That's the orbital period. Okay, so in fact, if be prepared that in this particular question, if I did not give you the speed, or if I didn't ask you for the speed, there's a way to directly calculate the orbital period by doing a little bit of algebra. Okay, so I'm gonna have a tag along question which I'm gonna write into the rest of my notes, which is not very ideal, but maybe I'll do insert a page here. So this is a bonus question, a tag along, and similar situation. We have the satellite here, okay, and there's the force due to gravity that is causing the satellite to move in this circular orbit. And if we write out the FNet equation, then that's going to look like big G, force due to gravity, is equal to the mass times the tangential speed divided by radius, which we can also write as, remember, that we can also write this as mass times 4 pi squared r over period squared, because all we did was we substituted v is equal to 2 pi r over the period into this equation, and that's going to give us this guy over here. So if I wrote out the whole thing, then my FG is going to be big G, big M over mass of my satellite divided by the radius of orbit squared equals to this whole thing, small m 4 pi squared times r divided by the period squared. And don't forget, mass here cancels out. Okay, in fact, I could also combine this r with this guy over here by dividing both sides by r. If I did divide both sides by r, I'm going to get big G, big M over r, not just a single r, this is a r cubed, because this guy got divided here. So I get, it would look like this. I have r down here, and I have another r down here, meaning I get r cubed. And so that's going to be equal to 4 pi squared over period squared. Okay, so this in fact has something to do with Kepler's laws, and which I'm not going to talk about in this video, but I'm going to give you a bonus question and something to think about. So this has to do with orbits around center, around a particular center. So my question is, okay, if my orbital radius, is quadrupled, okay, so it's multiplied by a factor of 4, then how much, by what factor, is my orbital period increased by? Then what happens to orbital period? So what factor does orbital period have to be increased by? Okay, so what that means is this guy over here, that's the orbital radius, this is going to be multiplied by a factor of 4. If this is multiplied by a factor of 4, then by what factor does your orbital period increase by? Okay, so that's the question. All right, so good time to pause the video. Okay, and that's it. So I will explain it here. Now, if my orbital radius is quadrupled, then I am going to get 4 times my orbital radius, and don't forget, all of that is cubed. So this is going to give me 4 to the power of 3. 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 64. So I'm going to get a factor of 64 on the bottom here, okay? And which means for my orbital period, in order for this equation to hold, the proportionality has to be the same in order for me to have a perfect circular motion of my satellite. So my equation still needs to hold, which means on the very bottom, of my equation on the other side for orbital period, I also need a factor of 64. Come on, blue ink. I also need a factor of 64 over here, okay, in order to balance out my equation. So to balance out this equation with a factor of 64, I need to figure out what does my period need to be multiplied by in order to get 64. So this is kind of the line of thinking. I need 64t squared, okay? So to get that, I need some factor, okay, that I multiply by my period, so that when I square everything, I'm going to get 64. So what squared gives me 64? If you're thinking about 8, you are correct. So 8 squared is going to give me 64. So if this is 8, okay, then I'm going to get 8 squared equals to 64, and then this is going to give me t squared. So the only way for my if orbital radius is multiplied by 4, that means my orbital period has to be multiplied by 8 based off of this proportionality factor here. Okay, so this is the this has to do with the orbital radius. It has to do with the radius orbits. Okay, so hopefully this bonus question gave you a chance to really think about the relationship of the orbital radius and the period. Phew! Hopefully this video wasn't too long. I thank you for watching, thank you for joining me, and good luck. Fan Mama Physics signing out.